Okay, so we're going to start on chapter 5 now, and just to give you an idea, some of the things we're going to be doing there is identify that center of gravity, explain the relationship between centroids and center of gravity, and then construct resultant forces of distributed loads. So we've been talking about solving, in chapter 4, solving for reaction forces and that sort of thing by virtue of having some loads on things. And what we're going to find is what do those arrows come from? So we're going to talk about basically where those loads actually come from and be able to construct them, figure out where they are. So we have a situation where, some forces are concentrated in the little arrows, and the vector mathematical approach that we use to represent that force is pretty accurate. But then there's going to be other forces, such as all of you folks sitting in this room here. We've got a distributed load. We're distributed across the floor here. The weight of the beams and that sort of thing are all going to be contributing to load, that sort of thing. And the problem is they're distributed. And what we need them in to be able to use our equilibrium equations, we're going to need them into some sort of vector form, right? So we can get them into x, y, and z components. So what we're going to be looking at initially is starting to look at this center of gravity. So we're going to have things that have weight. We need to figure out, okay, where is that weight acting? So I can go ahead and start calculating, say, for example, support forces and that sort of thing. So we'll just put the definition up. Okay, so a bunch of words there. What we're looking for then is we're going to be calculating the point at which the resultant weight of that body acts through. And if you go back when we were doing all that stuff with resultants, remember we calculated a resultant couple and a resultant force, and then in those perpendicular systems we were able to then just create it down or make it down to one force, the point where basically the couple is equal to 0. So that's the point we're going to be looking for there. So recall when we were doing resultants, we had our engineering body there. With a bunch of forces on it, maybe some concentrated couples acting on it. And we went through a process where we used that principle of moments, and we calculated the force couple at a place there. And then we were able to take that single force and move it to a point basically that created that same reaction here. But in terms of the body, then we're saying that the external reaction, everything that's going on in this body here, is the same from this one as it is with this one. So we're going to get the same sort of reactions there from those springs or whatever it may be. And Oops. R. And just remember, we were using this principle of moments. Moment is basically equal to the force times that perpendicular distance. So we use that to calculate, OK, I need to move it that far over, basically, and then my body will see the same sort of force couple system as if I had put it at this point. So what we're going to be spending time then is trying to figure out where that point is. Okay, CG is center of gravity, so my shorthand for that. Red go. I got one bigger. OK, so we'll consider a system of particles here. This will be like a mobile, something you put, your parents probably put over your crib, and they could tell you were going to be engineers because the first thing you wanted to do was calculate that point where that resultant acted, I'm sure. So the engineers out of the arts and letters kids drew them, made pretty colors out of them, knocked them around and stuff. But the engineers were the ones that actually figured out where that wire went. No, there's a weight up here, there's a bigger weight here, a little weight over here. Now the one thing we're missing is distances.
No, it's supposed to have 1, 2, 2, 4, or it's 3.
There's a 2-pound weight there, a 2-pound weight there.
Just kidding.
4-pound weight there, and a 1-pound weight there. But you did catch me, we need distances here, so 2 feet. Modern set of kids. I'll tweet you the answer. Okay. God, you're going to wear me out. Can't keep up with all of this. Okay, so again, here we are, the engineers. We're sitting there trying to figure out, okay, Mom, where should I put that wire? Because we're going to hang this, and what we want to be able to do is be able to, when you think about it, the hanger is going to keep it from rotating and that sort of thing, huh? The point where we have a resultant couple of equal to 0. So our resultant weight is basically the sum of all those forces. We'll call them in the y direction there. BB1 plus 4 plus 2 plus 2 equals 9 pounds. No hashtag. A resultant couple. Oh, the one thing I haven't put on here too. An important thing we need to put on here too, because we're going to be talking about measuring where that distance is, where that is, we need to form a basis of where we're going to do that. So we'll set up a coordinate system, and basically the key thing is that we're going to need to measure from that same coordinate system there. So we'll set up a coordinate system here so the origin's at that 4-pound weight. And we'll call that point O. So we'll just think about basically what's going to contribute to moment now at that point. And this is basically a sum of the weights times the x distance, because the y distance doesn't really matter in this case. The forces are all acting perpendicular this way, or acting vertically down, so I need the perpendicular distances, which are only going to be in that x direction there. So in terms of looking at that, well, I've got my 1 pound weight out here at 2 feet. So I'm going to go minus 2 feet over to get that one. Now, does this 2 pound weight contribute any moment to my point O? Does the 4 pound? So the only other one will be the 2 pound out there. And it's at 3 feet. So I got 4 foot-pounds in that direction there. And again, this is measured both those, everything has to be measured from the same point. So we're going to set up a axis system there and measure everything from that. And then we're going to describe where that resultant is based upon that system we've established. So then we use the principle of moments. And then just simply taking the moment, dividing it by the weight, what's going to be left in terms of units are going to be feet. And what we'll find is then, if I want to hang this thing, then I'm going to move it 4/9 over a little further than about a half a foot. And what we're saying then is that if I take my string, then I have a 2-force system, right? We've resolved it all to a resultant force there. And if I take my string, which will pull this way basically, what I'll have is a point then on that mobile that won't be twisting back and forth. It'll be hanging there, and then we as engineers can sleep peacefully. So this is a very, what we call the discrete form, or the principle of moments. And what I mean by discrete is that we have, known quantities. There's no integration involved. We don't have to shorten principle of moments to PM. So this is a discrete form. What we're going to be doing is we'll be looking at that, but we'll also be looking at the integral form of it. And actually, we'll start off with that here next. But the discrete form just basically means that it's a 4-pound weight. We know it's a 4-pound weight, and it's concentrated at a particular point. So when we set up the general approach to this, again, we're going to establish some sort of an axis system. Colors. So we'll have a body that'll have a fixed weight. And what we're going to do is look at an infinitesimal piece of that. And that portion, however small, will have a little bit of that weight, our dW. So we're going to take that. And we're going to have that ability now to do some integration, which I know you all will be looking forward to. Actually, though, the integration doesn't occur until next week. We'll do that on Thursday. Okay, so the general form involves integration. And we'll look that this looks like the principle of moments when we talk about it. It's the main weight there, and it's that distance that we're trying to find. And then what we're going to be doing is taking those infinitesimal little pieces, doing an integration across them, just like we did with the summation of the discrete form there. But each one of those, remember, has their own measure of moment there. So it's going to be a measure basically to that particular point. Okay, so pretty simple. That's going to be the weight of the body there. And then this x bar is the thing that we're interested in. And it'll be, generally in your book, this will be a capital X bar if we're looking for the location of the center of gravity of the whole body. And then similar. Same sort of thing when we look at that. Now, one nice thing is we can make some assumptions and actually make this a little easier, because summing up weights, integration of weights, is going to be kind of a messy thing. You're right. I just want to make everything infinitesimal. Thank you. Okay, now one nice thing, we don't necessarily want to do this sort of thing. Integration of weights is kind of a messy thing. But there's a couple assumptions we can make. This one's pretty easy to do. I mean, gravity's going to be acting. Most of the bodies we're dealing with are small enough that we're not really worried about them. Hoover Dam may be a little bit different, but and then also if we have uniform density. And the one thing, if we can make those two statements, if we can make those two assumptions on the particular body that we're looking at. So uniform density means basically it's made out of the same stuff. We're looking at a block of concrete or a block of wood. Gravity acting equally means we're dealing with something small enough here. We're not dealing with the space station and that sort of thing, big things. So the key thing is with that assumption, the center of gravity of a body is at the same place as the centroid. Now, centroid is basically the that point where it's the center of the volume, the area, the line, that sort of thing. And the nice thing is when we go to that point, if we're looking at just finding the centroid, we don't need any material properties. So I don't care whether it's steel. If I've got a body, if it's made out of steel, made out of wood, or styrofoam, it doesn't matter. All I need to worry about is those physical properties of volume, area, or line, and I can find the center of gravity of that particular body. So that makes life a whole lot easier in terms of solving for things. These messy equations now with W's and that sort of thing resolve themselves to just simply an integration across the volume. Integration across an area. 2D will be doing a lot of that. And then doing things like wires and that sort of thing, maybe bars and stuff, we might even resolve ourselves getting down to doing lines. Now, one thing we're going to pay particular attention to, we're going to spend some time, and your book has a whole thing on it, is this item here. Because there's going to be a lot of 2D stuff. This is what's known as the first moment of area. And we're going to introduce it here and play around with it a little bit, but you'll see a lot more of it when you get into mechanics and materials. This will be the tool that you'll be doing your shear calculations with and stuff. So get real comfortable with it because you're going to be seeing a lot more of it. The way we express it So either term, but the key thing here is note that your terms are different there. And again, think about moments again. Moments, we're talking about in terms of an x direction here, then what we're talking about is a first moment of area about the y-axis. The other thing, since we've already laid out the expression there, basically we can express it in terms of this, or we can express it in terms of this. So we've got the two different pieces there. The nice thing, we'll put this over here. We can use this when we start thinking about symmetry here. So if I have a piece on either side there, so I've got two pieces of delta A. And if I do a integration across those areas there, whoa.
4 and 5.
4 and 5. Just leave them here. Are they separated?
There's just 4 on top, and then it starts 5 alphabetically.
Okay, okay. We'll split it up at the end. And I got a prize for you.
Oh, I
Just,
don't know.
yeah, that's a little late.
Thanks.
All right, well, spend an hour doing that. Okay, again, now think about that first moment of area. Since it's only x, if I've got the same amount of area in the minus x area, on the minus x side of y, and I've got the same amount of area over on the positive side there, what we'll find then is that if I were to do a calculation for this first moment of area, what I'll find is when I do the first moment of area of that whole body, what I find is that it's 0 when I measure it from this axis system, from this y-axis system. Anyone know what that means? Symmetric, very good. But remember what my x bar looked like? It's like that, right? So what I'm saying is if this term goes to 0, and this is a tool we want to keep in our back pocket for sure. The centroid will lie on that axis of symmetry. So if there is an axis of symmetry, half your job's over with. In this particular case, if it looks like this, maybe if it looked like a pear or something, we wouldn't have it symmetric in that direction. But if we can find a line of symmetry, then we know that our centroid has to lie along that line somewhere. And that's one thing you'll see in terms of EIT exams and stuff like that. So you don't want to do a whole bunch of calculations you don't need to if you can find this line of symmetry to start off with. Another shortcut we'll look at is going to be composite bodies. So we're going to look at basically making this a little easier here. And what this is going to be is a combination basically of discrete form of the principle of moments and possibly some integration depending on what we do. So what we do with this So what we're going to do is break that body into simpler shapes. And the nice thing about the simple shapes is generally we're going to know where the centroid is. And if we don't, it'll be in the back of the book too. They've got a lot of the simple shapes basically back there. And what we're going to do is look for then, we're going to use that discrete form that we just did with the mobile there and the weights and stuff, except instead of weights now, we're just going to use areas. I'm going to use that discrete form And we can use areas or weights depending on So we'll look at an example. We've been given a particular body here. Where'd my red go? So I know my body at the rectangular piece there has a weight, and we have a center of gravity at that particular point. As a matter of fact, it's pretty easy to figure out where that one is because there's a line of symmetry there and a line of symmetry there. So the nice thing about a rectangle is we know it's going to be right in the center there. Two lines of symmetry, when they intersect, if it lies in the line of symmetry and it has to lie on both of them, it will be on that. So we got the line of symmetry there. And then what we'll find is we'll also have a center of gravity there for our triangle area there. It'll have a different weight. So this could be a body that actually has two different densities. We might have a piece of concrete and a piece of wood attached to it, or different material properties there. So we can look at those two different things there. And then note, where is that? The locations of those particular center of gravities can be measured by the y-axis there and by values there on the x-axis. And then other things we'll put in here is so I'll just get some information here. Okay, so basically my center of gravity for the first one there, the x1 will be half a foot. Now my distance to x2 is going to be the distance of the rectangle plus then the distance to that. And we'll show in triangles that basically the center of gravity is always going to be a third from the base leg there. Y1 will be up here since it's 2 feet, and again, centroid is going to be acting there. And then the y2 distance, again, it's going to be the 1/3 the distance up, basically since it's 2 feet high there. So it'll be 0.66. And then other information we need is the weight. So we'll attack this through the principle of moments. What we want to do now is find out where that one resultant force is acting there in terms of x and y. Okay, so setting up our equation of principal moments is going to be resultant times that distance that we're going to be measuring to, and then it's going to be the sum of those little pieces. In this particular case, it's just those two. So R is just simply going to be W1 plus W2. It's the weight of the combination. XCG is the thing we're looking for. And then we need to consider looking at the two pieces there. And it'll just be those pieces, the individual weights, times their individual moment arms. And then setting it up the way we want to set it up in terms of solving it is just simply we take this piece here, this one's here, and then divide by my weight there. And what I find then is that it'll be about 0.777 feet over. Do the same thing with y. And it'll be a little bit different because that center of gravity is a little bit different in terms of that. And then when we're done, this is what we're saying. This is the equivalent set of force systems. That's where I can take and put a hanger, and that thing's not going to rotate at all. Now, why I have them in different direction is think about it. If I were to take that structure and move it this way, where would I hang it if I rotated it over? Or if I put it in a centrifuge, you may have your forces acting out in that direction there in terms of the centrifuge. You need to know, OK, where do I hold that so it doesn't spin? So what we'll do is we'll just start tackling some of these problems. Sure you've got it all written down before I hide it. We'll be done writing before I hide everything here. OK, for our first problem, basically what we're going to do is we've been given a horizontal axis here. So we've been given a particular axis system to deal with. And we've broken it up in an area A1 and A2. And what we're going to do is calculate that first moment of area. One of your homework problems will be calculating first moment of area. So we'll get used to that. Again, this is something you'll be doing in terms of moments of mechanics of materials and that sort of thing, doing your shear calculations. Okay, so that's our object. And what we're going to do now is find, use another color here. Find that first moment of area there. So it's going to be rotating about this axis. We're going to find the q of x, and we're going to be using a y moment arm to get us up there. Now, again, to start off with, okay, so we got symmetry there. And what we're going to do is say, OK, then all I really have to do or really worry about is solve half of that. If I find the center of gravity or the centroid of that particular area there, or the first moment of area of this particular piece here, I'll also have it for that piece. There's symmetry there. So save ourselves a little time there. Well, that'll be the next problem, yeah. This is first moment of area. So we're just doing a first moment of area calculation. The next one, we're going to do the composites. So you're jumping ahead of me there a little bit, but. And as typical, what they're going to do is give you a problem where you have to do a little geometry beforehand. So the problem is I don't know what this width is here, right? So if we consider looking at just the triangle portion there, where's my green? What we're going to do is set up some similar triangles here. So what we got is we've got our heights here. If I consider just looking at this triangle portion here, OK, it starts off at 0 there. It's 24 over. If this is 72 across the bottom, then the base of this triangle all by itself then will be 72 minus the 24, or 48, 0.48. So via similar triangles, what we'll find then is OK, so we have 4, 8, which is the total triangle there. And then the partial triangle that I'm going to be doing, the similar triangle there, is only 0.84 height. The unknown distance then is that base there. This is the x bar. And we've got the x bar and the piece to go ahead and get started with this. OK, so that's my little piece here that I'm going to be looking at, and the necessary dimensions there. And we'll use YT for Y triangle and YR for Y rectangle. Okay, the location of the centroid, again, of a triangle is going to be 1/3 up from its base. So that yt then to that centroid of that particular area there is going to be 0.24. Rectangle is pretty easy. It's going to be at the halfway point. We know it acts right there in the middle. Okay, and then where we're going is calculating this first moment of area. .42. Did I miss something? Oh, yeah. Thank you. And what we're going to do is take advantage of this discrete form. I mean, if I'm really interested and excited, I can go ahead and do the integrations. But I'm going to use that other portion of that equation there. And I'm just simply going to use this discrete form and basically put it together as a set of composites. OK, so my y of t is going to be, why am I? Yeah, golly. I'm reading the wrong page here. OK, so we've already done that calculation there. The area of the triangle then will be 1/2 base times height. See if I can get these numbers right. And then the other piece will be the y rectangle. And that's just simply, again, the base times height, or one side versus the other. Oops. And I get for that 0.1176. But again, remember, this is symmetric half, so I need to make sure I do both sides. So I'll times it by 2. Just simply times it by 2. And that's my first moment of area then of this particular piece then over this axis there, the x bar, using the x and the y axis as shown. OK, so that's first moment of area. The next piece we're going to look at is then start to look for those centroids. So we'll have another interesting problem here. Oh, and just to finish up that problem, if you were to work the bottom and solve for the bottom, I know the problem asked for the bottom, it will be the same number. So it'll be 0.235. And what does that mean if it's the same number? No, first, what we're saying is that the first moment of area will be 0.235 for the bottom also. What does that mean?
Centric in the middle, center of mass in the middle.
The centroid or the center of mass will be in the middle there. Because again, the area on this side is, the first moment of area on this side is the same as the first moment of area on that side. We have a positive y-arm this way, we have a negative y-arm there. Sum up to be 0. which then when we go back to our solving for the centroid area there, or the centroid, it'll say it's equal to 0, which means we're on the centroid. Or the centroid is on that. Now what we're going to do is a interesting problem where it's just going to be basically a quarter of a circle there, and then we're going to cut out this section there and then figure out where it acts. Question?
Would it be inches squared?
I beg your pardon?
On the left row?
No, because I think it's y times a, right? So area is already squared, and then you're adding another one, so it's going to be y to the third. That's a good point, though. We didn't bring that up. You know you're solving a first moment of area. It's going to be in terms of length cubed, okay? And we'll get into second moments of area, which will be length to the fourth. But again, keeping those units there helps you along there. If it's in something else, if it's in inches squared, then you've missed something. You've missed a moment arm usually. Okay, so now what we're going to do is try to use that first moment of area there and start locating centroids for interesting little areas here. But this one's interesting because it's an area that's composed of something that's solid and then something that's taken away. Wish we could have. Wish we could take that off the side there. I keep feeling like I'm a moving man here. Okay, so anything unique about the problem to start off with? Any hints or clues that we can work with? Yeah, there we go. We got some symmetry going on there. Now, it's not on an axis, though, right? It's on a 45, but c'est la vie, we can do that. So good point. Symmetry. Will be on the 45. Now, what we're going to do is consider the two pieces. So we're going to consider the quarter of the circle there. And what we're going to do then in our composite areas, though, is we're going to subtract that little rectangle. And the trick is what we're going to do is we're going to treat the whole as a negative weight or a negative area.
Is the square the whole?
Yes, good point. In terms of our looks like that, right? So this is what we're really looking at there. We're trying to figure this out. Let's get some dimensions up there so we can talk about it. So the radius is 10 inches, and then we've got a 5-inch square cut out of it, like so. Now, what we'll find is especially with these composite areas, it's going to be much easier to set it up as a table. So we're going to, might want to let me start across so you can see how much room you're going to need. So we got 1, 2, 3, 4, 5, 6 columns. And what we're going to do is then sum up the columns. Again, this is a discrete form. So note that what I've got is my moment arms here to those areas. And then I've got my first moment of areas here, right? Inches cubed. So we've got those laid out. OK, so the area of that quarter cube is going to be a quarter pi r squared. Pretty straightforward. So it'll be 78.54 inches squared. Now, we'll find the centroid of a quarter circle there. Most of this stuff is going to be in the back of your book here. So you're going to be able to use that. And again, in terms of, since we're not doing this on this exam, don't worry about it. But I will give you those sort of things so you don't necessarily need to copy the book, basically, in your cheat sheets. So what we can find, is without going through the proof there, is that to find that centroid of that particular area there is going to be there. It's going to be 4r over 3 pi, a real nice, easy number to figure out. And since it's symmetric there, basically it's going to be the same whether I'm measuring it from the y or the x. And then what I'm going to do is take that number and multiply it times those and put it in this column. And there's my first moments of area. Now the next piece I want to look at is my square, my whole. But again, this is where the trick comes in, basically. Now it's going to be a squared, or 5 times 5. But I'm going to call it a minus 25 now. So I'm going to treat it as a negative area. Now, I need to locate the centroid of that particular piece there, which will be about there. And since it's got 2 axes of symmetry, I know exactly what that is. It's going to be 2.5 either direction there. And then I'm just simply going to multiply those 2 together. But I'm carrying the sign because that area was negative. Question?
What is that moment, what does that like represent really? Like other than just what is this number? Is it like the distance you have to be away from an area to balance it out? Like what is that?
You're talking first moment of area?
Yeah.
Yeah, this guy. It's like that. It's actually, it even goes to second moment of area when we do that. But basically, yes, it's measuring the area that's away. Probably the best way to think of it, and when you get into mechanics of materials, you'll understand why we have I-beams instead of just having a solid rod. Because when we think about bending, if we can get area away from the center, it does more work there. And that's why we have big I-beams on bridges and not a rod or something like that. So it doesn't make a whole lot of sense right now. But yes, basically it's a measure of area away from that center, from that centroid.
Is that the one that means like how easy it spins, kind of, something like that?
Yeah. Actually, when you get into second moments of area, basically that's also related to, they call it moment of inertia.
Okay.
So yeah, same sort of thing in physics. And as a matter of fact, we still call it moment of inertia, although it's really second moment of area because we're using it in terms of area. But it comes from that same concept. OK, now, question?
I must have missed a step, because if r is equal to 10, how do we get 4.244? Or radius is 10.
So 40 divided by 3 divided by pi, that's divided by 9 or so.
My calculator's coming up.
Yeah, you got to make sure when you do pi, you can't do 3 pi at once.
Yeah, well, pi is about 3, right? A little bigger than 3. So we got 9. 9 goes into 40. You know, that's around 10, and it's got to go in around 4 times. So fundamentally, it's pretty close, I think.
I got that.
Did you? Okay. Okay, now the trick is at this point, why we develop the table is then we're going to do this. Question?
I was just wondering where the 4R over 3 pi came from. Is that what you're talking about?
The back of the book, basically. It's already solved for us. I'm not going to go through the proof of it and for you and that sort of thing. So we're going to be able to use that, and again, when we do tests and stuff like that, I'll provide you that information and stuff. Okay, so the key here is then why we built it into this column format is then we can sum it up and basically do that discrete form. Notice that the area of this thing is going to be the area of this subtract the area of this. We got the minus sign there. So that should be the correct area. And then in terms of first moments of area, we're going to just sum those two up, and they're both the same thing. So what we do with the table form is actually just doing an application of the discrete form of this. And what we'll find is then just simply going through the calculation is going to be the same for both, but it's just simply taking that far column, dividing by the area that we summed up. So we're basically taking these numbers now, our discrete forms here, we've summed these up, and we just simply do a nice simple division. And a key thing is that they're both the same distance, which then it meets our criteria there in terms of lying on that 45-degree line of symmetry. A little bit of time left here. We'll go through one more problem. Okay, did you guys, I don't think we got this one in the handouts. Did we get this in the handout? Okay. I'll let you copy it down a little bit there. It's in the book, though, too. If you've got the book, you can pull it. This is going to be, again, a discrete form because, again, what we've got is measurements of length here. We've got an iron rod, basically, that we're going to be hanging. And we want to hang it at some point in that point C. We want to choose that particular L there, such that it BCD remains horizontal. Basically, it doesn't twist. And what I can do is, don't cram yourselves too much. I'll post this, so you'll actually have the problem and everything on it and stuff. So I'll post it on the web later tonight or tomorrow. Actually, we're going to be here late tonight. So what we're going to do is basically find that, but we're going to, again, use a discrete form there, and we're going to use now those lengths. Now, a couple of things to note that you probably didn't copy down because you were trying to get all the dimensions down. It's a homogeneous wire, okay? So that means it's the same density throughout. So again, I can find that CG, or I can find the center of length in this particular cases. What we're going to do is determine the center of gravity of each of those lengths, and then we're going to just sum them together like we did with the composite form there. Okay, why do I only need horizontal distances? Because it's hanging, yeah, we're talking about something that with weight. So the weight's acting down, basically. So all I care about in terms of my moment, my principle of moment, are going to be those horizontal distances. So what I'll do is just simply go through each piece. I need to get a better pen. This one works. Okay, so this particular straight piece, again, since it's homogeneous, it's the same thickness throughout, then my weight will be acting in the center of that particular piece. I need to get some information, however. Okay, so my distance to that particular point there, or the measurement from that to C, basically, is going to be the 40 millimeters. So this is where I'm going to be setting up my moment, because it's going to be twisting about there. No, just my moment arm to that weight. So I'm measuring here from that pivot. Remember my pivot there at C, and I'm measuring that little local moment arm there, but instead of a first moment of area, it's a first moment of weight, essentially. Okay? It'll make sense when we put it together. And that won't make a whole lot of sense until I put those dimensions up. But we've been given dimensions there of that. So in terms of calculating the length, I just simply do the Pythagorean theorem. And your author, of course, made it very nice and easy. And then the weight is going to be 100 times whatever the weight is, the density and that sort of thing. But right now, what we're going to find is that we're going to be able to subtract that out, or be able to divide it out. But basically, that's the information I need for that particular piece there. The weight of that piece, the moment arm to that piece, and then the length basically help me get that. And we're cutting it close here. Do one more piece here real quick. That was the most complicated one. We'll just do a real quick piece here. The other one's very similar, basically. So And the two pieces we need there is basically the moment arm to that particular piece from C, which is 40 again. And then the weight will be 80, the full length, then times whatever the weight of that is or density of that is. And what I'll do is since we don't have to worry about it for the homework, you're not even going to want to look at it until next week. I'll go ahead and post it. You can take a look at it there.